Hi everyone. Hi. Can we sit a little closer? We're starting with the sessions.
Are you present?
Yeah, he needs the extension.
Cool. Good morning. And yeah, we are on to do this for ZK Bankai and I work at Polygon, apparently. So that's an addition. So morning. We started with a few sessions, starting with Guni, who is a part of Bankai. We'll do a session on NPCs. So over to you, Guni.
Awesome. So you all know what NPC is, right? The idea behind NPC. Does anyone not know the idea? Okay, great. So with this session, I hope to give you the intuition behind how NPC actually works. So so largely the problem of NPC is that there are two parties A and B. They want to compute in a function f of A and B. A and B are the inputs that both of these parties have, and they want to compute it without trusting a third party, without sharing the data to the other person. So now largely there are two techniques used to do this. One is called secret sharing and the other is based on carbon circuits. So today I'll be focusing on how it's done with secret sharing. With this I'm planning on taking a practical example of say if you want to compute A plus B into A minus this is the function that you want to compute, and A is the value that A has and B is the value that B has. So how do you do this? So, for this example, we'll be operating in a field of 7, the finite field of 7. So, in this case, say 3 plus 5, which is 8 in a general decimal system, it would be 3 plus 1, 2, 3, 4, 5. So, 1 would be 8 mod 7, which is 1. Right, makes sense. Yeah. Question we can ask about goes to. This can be split into an addition and a multiplication problem, right? So first you need to add A and B together. So how do you do that, right? Without sharing A and without A having to share his data and B having to share his data. So step 1 is randomly sampling. Individually what happens is A first will go to what each of these parties do locally, and then how they get the data from the other person. So what A does is randomly samples a value from this set. So say for example if the value that A has is 3, and the randomly sampled value turns out to be 4. So let's call it I mean, with the once the random value has been sampled, so the random value is 4 here. A calculates 3 minus 4, subtracts the value from the original value, which turns out to be 3 minus 4, 1, 2, 3, 4. So 6 is the value that A has now. The value that he got from subtracting his original value with the random sample value. So notice that 6 doesn't reveal anything about what the original value is, and this is the value that A will share with B. And similarly, B does the same with this value. So say the value that we had is 5 and the randomly sampled value is 6. Now 5 minus 6, like 1, 2, 3, 4, 5, 6, which is again 6. So now we have like 2 random values which are like shared with the other person. So right now. So yeah, like after this randomized has been sampled, I'm just saying either R1 and R2, 6, and cool. Now these values, these randomly generated values are what we work with now. So to calculate A plus B, which is the original prompt, like A plus B is what we need to calculate. Yeah. Random value 1 is shared with yeah. So yeah. Right. This is a mess. To calculate A plus B, right? We're just like bouncing out of yeah. Okay, now, Saurabh, you want to continue from here?
Yeah, I can. Maybe I'll have to share my screen. What do you have?
Sorry?
You want to try the conversation on this?
Oh, it's very messy. Thanks.
Alright, cool. Hi everyone, good morning. I'm Saurabh and I'm going to be presenting my work on fast, performant and private transformer inference using MPC. I know those are like tons of words and hopefully a lot of it makes sense in the next 10 minutes. Right, so just before I start, like a quick show of hands, who here is like familiar with the transformer architecture in AI? Alright. Okay, maybe another question. Who here has worked with a lot of these chat-based applications like ChatGPT, GitHub Copilot here? Yeah, almost everybody, right? And these are great, of course. And a lot of this AI revolution has happened based on this model called transformer, and this is essentially a neural network architecture that lets you train on massive amount of data in a parallelized manner, in a very, very fast manner, right? So you can, so this wasn't what people thought how, so this is the architecture that gets run behind a lot of these cloud-based AI inference services, right? Like GitHub Copilot and ChatGPT. But a lot of these create privacy concerns, right? So the way, for example, let's take GitHub Copilot for example. So the way it works is you use your favorite ID and you send your code to the server. The server then runs the inference on the prediction, on the kind of code that needs to go next, and it sends the code back to the user, right? So this is the general workflow. But you kind of have a big trust assumption on the AI model provider. So this is OpenAI for this case, but it can be any sort of AI inference provider, right? So there are a lot of privacy risks involved, and this is not just for chat-based models. This is for AI, any AI model right, in general. So how can you solve this? So we need a way to solve this privacy issue of having these AI inferences done, and we use a lot of these MPC techniques to achieve this. Right. So what happens here is we essentially transform this into a two-party computation mode wherein the user's prompt is encrypted and the model is encrypted as well, and both the parties come together and eventually generate the next token prediction, right? So I want to highlight the important point here that it's not just the case that the user prompt is encrypted, it's also the case that the model weights are encrypted as well. So if a model provider wants to protect its source, right? If there's a proprietary model that doesn't want to open source the data, this has a way of the person releasing the model as well. And both these parties come together, you can generate a private inference using these MPC techniques. Right, so hopefully you kind of got intuition around one of the techniques that's super important with this from Gumit's previous session, and it's called secret sharing, wherein both the parties have these encrypted inputs, but they don't share those these inputs in the raw format with each other, but they rather communicate among each other using this technique of secret sharing, and eventually they come together, collaborate, and generate the final result. And the problem with this approach is if you just try to throw this generic MPC tool at like a neural network model, right? It's extremely inefficient because so if you go down into the neural network architecture, there are a lot of operations that happen. I'm sure you all know that matrix multiplication is a big operation that happens over and over again, right, in this large language models. But then there are these other layers as well, which are called activation functions like LU and softmax. And unlike matrix multiplication, these are non-linear, right? So in MPC, you ideally want only linear computation to be done. You want to avoid as much non-linearities as possible. So this is, although this does not get used much, this you can see from the numbers, most of the time is spent on just these layers, right? So you need some way of bringing down the time here, right? And so for a normal model, if you just throw a normal MPC tool at it, it will take over 60 seconds to run an inference, which is terrible, right? With something like OpenAI, you're expected to get the result back in under a second. So we need to optimize this in some ways. right? So the way we do it is, we don't actually use the formulas for GALU and softmax directly. Instead, we use the approximated version of these layers. So internally, these layers, right, they have this exponential function, which is a non-linear function that runs over and over again. So rather than using this exponential function, you approximate that using a quadratic form, right? And this is much more amenable to MPC computation, right? So if you take a look at some numbers, if you just use the raw GALU, which is a non-linear function, it takes about 11 seconds. But you apply this approximation technique, and it brings it down to like 0.5, like a 20x improvement, right? So similarly, the same technique has been applied to the softmax layer as well. So you bring it down from 40 seconds all the way down to 3 seconds, right? So this sounds great, but it also brings some drawbacks with that. Obviously, the accuracy of your model goes down a little bit. So let's say your model was performing with 82% accuracy, you just apply this transformation, the accuracy dips to about 63% for this data set called blue, right? So this is not the solution. This is a part of the solution. You need to apply another technique to make the model more performant. So with this, you kind of achieve high speed, but you kind of also want high accuracy, right? So there is another technique that we adopt, and it's called knowledge distillation now, right? This is the second technique, which kind of makes the whole thing come together and makes the whole thing more performant. Right? So this is like the internals of the transformer, and I wouldn't go into it right now, but just to give you an intuition behind this technique, right? What this basically tries to do is, imagine this is the raw model without any kind of approximation, the vanilla model, and this is yours, and let's call this the teacher model. Okay, this is the V1 model without any approximations, and this is the model after the approximation. Let's call this one the student model. Okay, so what we are basically trying to do is we are trying to distill the weights from every intermediate layer onto the student model. So we are trying to kind of match these two as close as possible, right? So we run a normal training loop like it happens in machine learning training, right? To decrease the difference between every individual layer here, right? And eventually, with this technique of knowledge distillation, you can actually achieve the same level of accuracy that you had with the initial model, right? So just to put everything into perspective, right? So this is like the whole architecture. So you start off with the vanilla treated model, you apply some approximations to make it faster, but then you lose out on the accuracy, and then you apply the second technique of knowledge distillation to get back the accuracy as well, and then you run the MPC engine over it to achieve these privacy guarantees that you want, and yeah, at the end you can use it like any other tool like ChatGPT, right? At the end. Yeah, and these are some benchmark numbers, right? So the TNDRS, with all of these optimizations, we can achieve up to 5 to 6x improvement compared to the vanilla MPC for the transformer model. And in my opinion, there are a lot of other things that are underexplored, and this number can be brought up even more. So yeah, that I'll be looking into a lot of other optimizations. And the code is public, and it's still worked upon, but yeah, you can take a look into this. And yeah, that's it. Thank you so much.
Any questions?
So that second round where you're coming back, I forgot the name of the technique or the slide before that. You're essentially
That's correct.
But yeah, just to finish this off, I have to settle down now. So the goal is to perform this addition here, right? So A plus B is what they need to perform. Let's call the first random value R1, which is sample, and the original value minus R1 is the second random value. So each party has two random values. Now A has R1 and R2, and B has R3 and R4. Now to calculate A plus B, what A does is shares the first random value with the second party. So B is left with B has 4 from here, and similarly B also shares one random value to A. So finally A has R1 and R4 from B, R1 from itself and R4 from B, and B has R3 from itself and R2 from A. Now they locally compute R1 plus R4, these two values, and R3 plus R2. And once this value is got, they share it with the other party, and finally this result, it comes out to be it preserves additive homomorphism. So the result is the same as what the original computation of A plus B would have been. So if we have to do that, so 4 plus 6 is 10, and 6 plus 6 is 12. So 10 plus 12, that's 22, and mod 7 of that is 1. So yeah. It turns out to be the same value. That's how. If you have any questions, I'm happy to answer. Yeah, sorry for the. Yeah.
In this paradigm, do we have operations? What limits do we have on the mathematical operations?
So addition and multiplication is typically what we can do with this technique. So with multiplication, it's a bit hard. You need to use something called Beaver's triplets. You need to generate 3 more random values to perform. Multiplication is much more expensive than addition. But addition and multiplication is typically what you can use.
Does this work?
It's way too loud. Very good for the recording. Recording might have had me falling. So thanks for the session, Guneet and Saurabh. The next session is from Jody, and we'll be talking about proofs and aggregation layer. How is the aggregation being done? Yeah. I'll invite Jody to come on the stage and probably talk us through.
Well, as you know, the aggregation layer is very much the technique for when you have many chains, many roll-ups. The idea is to communicate, or if you want, transfer value between one chain and the other. This is based, so the basic thing is what we call the Langstroth average, but at the end is reach. So when you deposit, we're working, for example, in Polygon, the first thing you do is you deposit you deposit the funds. Okay? And these funds, they are assigned to a network, to a roll-up, okay? And then you can move roll-ups from one to the other. Okay? And let me explain a little bit how it works. Okay? So if we start with layer 1, so we have what we call, we have a tree. That's an append-only tree, it's like kind of a database. So every time we do a deposit, actually we create a leaf here. And here in this leaf, what we are saying here, okay, we are saying maybe the token, you know, the address of the token, maybe Matic, USDC, Ether, whatever. Token address if you want. We have also the token origin. In this case, it's going to be layer 1, so it's going to be 0. Okay. We have the destination, the destination layer. The origin is going to be layer 1. Destination layer is the Indian rollup. Let's say we are going to send it to rollup A. Okay. Of course, here there is an amount. Sending 10 matics, 10 whatever. And there is also, let's say, destination address, or if you want some other messages that I can pass with this transfer, something that's specific to, so when you are depositing there, so what you want to do with these tokens in there. Okay, so there's the destination. I put destination address, maybe something else, a message or something else. Okay? So this is every time that I do a deposit in layer 1, actually what I'm doing is I'm creating one of these. So it's just an append only. I'm just creating the tree, and it's a tree that by smart contract the only thing that can do is just increase. So every time I'm putting a new leaf every time that I'm doing a deposit. Okay. So if this is the state, and this state, the idea is that this state in the rollups, this state is available. So in the rollup, this state is embedded or is included in the layer 2. So what we do is we put that state. So we put this root. Okay. We make them available in the rollup. Okay. So in the rollup, mainly what you do is you have a smart contract where you have the root of this tree, so you can prove maybe one of the leaves. So then what I do is, okay, I see that there is a leaf that says that 10 matics goes to this address. I create a bracket token that represents in this case the matic or whatever token is in there, and I send it to so you claim it in the user. And of course, I say, okay, this leaf, I already use it, so you cannot download, you cannot claim these fonts again. Okay, this is, okay, so this is, and for withdrawing, from going from L2 to L1, you do exactly the same. In L2, you have a tree, okay, we call it local execute. And every time that you send deposits to layer 1, actually you create a leaf. In this case, the token address is going to be the same token address. The origin is going to be the L1 because it's the token that you are sending. Destination rollup in this case is going to be the rollup A is going to be the L1 as another network. Or if you are sending to another rollup, it's going to be a different rollup. The amount, destination address, what you want to do in this other network, and maybe some messages. So this is exactly the same, even if it's layer 2 or layer 1. Actually, this is what we call a local execute. This is the local execute of the layer 1. This can be the local